Let's take a look at logarithmic functions and their graphs. So let's define it first. A logarithmic function is the inverse of an exponential function. So in the last section we took a look at f of x is equal to a to the x, or y equals a to the x graphs, and they looked something like this. And they had y equals 0 asymptote, and they went through the point 0, 1, or they went down for those half-life graphs. Well, now instead of y equals a to the x, we're going to look at x equals a to the y. So these are inverses of one another. And they're inverses because I've switched the x and the y values. Now, if I solve for y, what I end up getting is an equation that looks like this. Y equals log base a of x. And a is the base and y is the exponent from my other equation. Now, why can it be rewritten as y equals log base a of x is what we're studying this unit. So basically, logarithms are inverses. It's going backwards in calculation from exponential functions. So let's just take a look at that before we come back to what this graph looks like and what the inverse looks like and things like that. So a couple of little asides about logs. First of all, if logs are base 10 logs, which means the original equation up here was a was 10 to the x. So if they're base 10 logs, we actually don't write the base when we write out logs. So for example, if you were ever asked to write out, say, log of 12, log of 12 is the correct way of writing that out, not log with a little base number of 10 of 12. We never write that 10. If it's base 10, it's just assumed to be log 12, that's base 10. If logs are in another special base, you'll see this in calculus if you take calculus next year, and if they're base e, and e is a special number, kind of like pi, except e is like 2 point something. If logs are base the number e, we don't write out the base number either. Instead, for example, if we write log base e of 20, instead we would write ln, which means the natural log of 20. So whenever you see a base of 10, rewrite it as without the base there. If you don't see a base in here, then it's automatically 10. And if you ever see the letters ln, or even on the graphing calculator, if you see the letter ln, that means log base e. Most of the time we're going to be working with other kinds of logs, log of 2 and log base 6 and things like that. So we do need to have this as a little bit of an aside, just as the notation. So let's just skip ahead here and work with some logs and what they mean, and then we'll come back and look at those graphs at the end. So I said that log base a of x is equal to y is equivalent to a to the y is equal to x. And assuming that that's true, which it is, it's the definition of a logarithm, then can we change each of these questions to an exponential form? So this left-hand side is called a log form or logarithmic form, and these are the equivalent exponential form. And what we need to be able to do first is to go back and forward. So if I tell you it's log base 5 of 25 is equal to 2, the reason that that's true is because the base is 5, the exponent is 2, is 25. So if I say log of 1000 is equal to 3, this is equivalent to saying base is 10. Remember, when I don't write it, it's 10. Exponent is 3, and that's equal to 1000. If I do the opposite to this, and instead of changing to exponential form, I change things to log form, this is what it looks like. So the base is 2, so it's going to be log base 2. The number is 32, and the exponent is 5. And then if I ask you to actually do some math, let's see if we can calculate log base 4 of 8. Well, to calculate log base 4 of 8, I need to think about the equation that this is asking me for, which is 4, that's the base, to what power is equal to 8? Well, sometimes those are easy questions to answer. This one isn't. So if I gave you log base 10 of 100, and I asked you what that's worth, you would think about that as 10 to what power is equal to 100, and you'd say, oh, that's 2. And sometimes they're not as easy to answer, like log base 4 of 8. 4 to what power is equal to 8? Well, 4 to the power of 1 is equal to 4, and 4 to the power of 2 is equal to 16. Maybe it's 4 to the half, or 4 to the 1 and a half. But you can try numbers like that and see if they work or don't work on your calculator. But there's a much more efficient way of doing these, which we'll be learning later in this unit. But with this information, we can go back now and take a look at some log graphs and see if we can sketch them. So we're kind of doing two a little bit disjointed things here, and I've jumped back and forth. But one of them is to try to understand a little bit about these logs, and we'll definitely be doing more of that this unit. And another of them is to understand what these graphs look like. So let's jump back to the graphs. And remember, they're inverses. So if you have one of those graphs that's going up this way, and it's an exponential graph, the inverse is, there's a couple different ways to do it. You can either reflect it over the line y equals x, or you can switch all the x and the y values. So you know, for instance, there's 0, 1, you can switch that. So you know that it goes through 1, 0, and you can kind of see that with the reflection as well. You know that there's an asymptote for the original graph at y equals 0, so now there's going to be an asymptote for this graph at x equals 0. And it gets closer and closer as you go into the x negatives, so it's going to go closer and closer as you go into the y negatives. And then this is going to scoot off this direction. So I haven't got a super accurate graph, but this green graph is the graph of y equals log base a of x. Now, if your original graph didn't increase, if instead it was like a half-life graph and it came down this way, it would still go through the point 1, 0, 0, 1. And the inverse over the line y equals x would still go through the point 1, 0. Now the asymptote goes closer and closer and closer as you go into x positive, so the asymptote goes closer and closer and closer as you go into y positives, and then this one would go this direction. So we've got one log graph if a is greater than 1, and we've got a different log graph if a is got to be bigger than 0, and in this case less than 1. And with that information, we can sketch either of these graphs now, y equals log base a of x in either of its forms with, transformations. So let's just take a look at one of those. So we'll sketch y equals log base 4 of x minus 1 plus 3. So you might want to start with, okay, well, what's the exponential graph? This is equivalent to base 4 to some power. So if I were graphing y equals 4 to the x, it would look something like this, because the base is bigger than 1. It would go through 1, 0, and at 1 it would go up 4, and at 2 it would go up 16, and at negative 1 it would only go up a quarter, and my scale's not great here. So the inverse of that looks like the inverse directly above it. It's going to go something like this. In fact, at negative 1 it's going to go over a quarter, and at positive 1 in the y direction it's going to go over 4. So instead of 1, 4, it's going to be 4, 1. and then it'll be like 16, 2. And then the whole graph is transformed according to these two transformations. And so the first transformation is the x direction, and it's right 1. And the second transformation is the y direction, and it's up 3. And so you'll get a final graph that the asymptote will move right 1, so it will be at positive 1. And this point will move, the old point of 1, 0, will move right 1 and up 1, 2, 3. And this point of 4, 1 will move to 5, 1 and up 3, so it'll be at 5, 4. And again, my scale is not perfect, but I do have points that I know that it goes through really nicely. So of course, if I weren't just sketching this quickly, if I did it on some graph paper, it would look a lot more accurate, but we're using the ideas from Unit 1 on transformations to be able to transform any of these new graphs. That's it for today.